All right, so we're going to do some related rates problems. And this thing here, it's in your book. I probably handed it out to you. But these are some nice steps to kind of follow when we're trying to do a related rates problem. And we'll discuss them as we go along. So let's start with this one. This is an example from the book, so I figured it'd be good for you to hear me do it as well as be able to read it in the book. And I'm going to do my normal method of like always trying to start with a picture. That really helps me out a lot, and I think it'll help you too. So it says, a hot air balloon is rising straight up from a level field. Okay, so here's my hot air balloon. And it's rising straight up from a level field. And it's being tracked by a rangefinder 500 feet from the liftoff point. So here is the liftoff point right there. And my rangefinder, I'll call this right here, rangefinder, is over here. And I know that this distance right here is 500 feet. At the moment, the rangefinder's elevation angle is pi over 4. So that means if, as I'm looking over here at the balloon, this angle of elevation, which I'm going to call theta, so theta is equal to pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So a couple of things. When we're talking about related rates, what we're trying to find is how fast is something moving in relationship to something else. So I'm going to start out by always, what am I seeking in this question? What am I seeking? Well, I'm trying to find out how fast is the balloon rising at that moment. So let's give this balloon elevation here a letter. Let's call it A. Now, I don't know how big A is right at this instant. I might be able to find it out, and we'll deal with that later. But what I'm seeking is dA to dt. I'm seeking the change in A over the change in time. So in this particular example here, I'm looking for the change in feet per minute. And when you're doing these related rates problems, they're always going to have something to do with time, because that's what we're talking about. We're talking about the change over time. So I'm seeking dA to dt. What do I know? Well, I know this distance of 500 feet. Let's call it b. I know b equals 500. I use b because I can see I got the base of a triangle going on here. I know theta, because theta, they told me, at this moment is pi over 4. Now I'm going to make a little notation here. I know that b is 500 feet, and I'm going to put a bracket around it because that is constant. That is not changing. Theta, on the other hand, well, you can kind of see as the balloon goes up, that angle is going to change. So theta is not constant. Theta is something that is changing. What else do I know in this diagram? Well, let's think here. If I know that theta is pi over 4, right, this particular moment, I could probably calculate what A is at this particular moment, and I could probably calculate what the hypotenuse is at this particular moment. This is my hypotenuse. I'm not so sure I'm going to need to know that right now. But the other thing I do know that they gave me that is very important is I know that d theta to dt is equal to 0.14. So for right now, those are the things that I know, and this is the thing that I am seeking. So I'm kind of understanding number one, I'm kind of understanding the problem. And number two, I'm beginning to develop a mathematical model of the problem because I made a picture, I can see I got a triangle going on here. I'm thinking maybe I'm going to use a little bit of trigonometry. And I have made very clear what are constant quantities and what are changing quantities. Because we can only use constant qualities at the beginning. You'll see why in a minute. So now I need to look at number 3. I need to write an equation relating the variable whose rate of change I seek with the variable whose rate of change I know. Well, let's go back to our problem. I'm seeking dA to dt. I know d theta to dt. Now, is there a formula that I can use that relates A to theta? That's what I'm looking for. The variable is A, and the variable is theta, and I want to see, can I relate those rates of change to one another? Well, I do know something that might work here. I know that the tangent of theta is going to equal opposite over adjacent. So it's going to equal A over 500. Now, I can use this 500 because it is constant. It is not changing. A, on the other hand, that is something that's changing. So I can't really just plug in a number, even if I could bother to find it right now. I can't do that because that's going to be changing. So to make this just a little bit more manageable, I know that A is equal to 500 tan theta. I just multiplied both sides of this equation right here by 500. So I'm kind of set up relating the variable whose rate of change I know with the variable, I have the variable whose rate of change I'm seeking with the variable whose rate of change I know. So now what I'm going to do is I'm going to differentiate both sides. And I'm going to do this very consciously, going d to dt of that and d to dt of that. So this is dA to dt, which, as you will notice, is exactly what I am seeking. And this, well, I have a constant here. I'm going to pull that through the derivative. So I have 500 d to dt of tangent theta. So what I need to do is take the derivative of tangent theta. So I have 500. Well, I know from looking at my little formula sheet that the derivative of tangent theta is secant squared theta. But you have to remember, and this is where people get messed up, is that theta right here is another function. Whatever theta is a function. So I need to take the derivative of theta. I'm using the chain rule. So I take tan theta times d theta dt. Theta is a function of time. If I come back up to my diagram, remember, this theta here, as time goes on and the balloon gets higher and higher, this theta is going to change in relationship to time. So I have to multiply it. It's like the chain rule. I got to do the outside function, which is tangent theta, which gives me secant squared theta, times the inside function of theta with respect to time. So now I have a nice formula, dA dt is equal to this. And now that I've got this nice formula relating the rates of change of the variables, now I can start plugging in some numbers. So I'm still seeking dA to dt, and that's equal to 500. Well, secant squared, well, I know that theta at this moment, which is what I'm looking for at the moment the angle of elevation is pi over 4. I know at this moment I got secant squared pi over 4 times, well, d theta dt, they gave that to me. That was one of the things I know. That's right here. So that is times 0.14. Let's do a little bit of calculation. Well, that would be 500. Now secant is 1 over cosine. So let's go 1 over cosine pi over 4 times 1 over cosine pi over 4, because cosine pi over 4, I'm sorry, I've squared it right here, times 0.14. So I have 500 times, well, that's 1 over, well, cosine pi over 4 is radical 2 over 2, radical 2 over 2, times 1 over radical 2 over 2, times 0.14. So I have 500 times, well, that's a reciprocal right there, so it's 2 over radical 2, times 2 over radical 2, times 0.14. So that is 500 times 4 over 2, well, that's 2, times 0.14. So I have 500 times 2 times 0.14, which is equal to 1,000 times, let's not use x, times 0.14. And when I do that times a decimal, I just need to move the decimal over 3 times. So my answer is 140. That's my numerical answer. But I have to look and see, what was the problem asking me for again? I want to know, how fast is the balloon rising? And it's being measured in feet, feet per minute. So that's when I'm not doing feet per second, I'm doing feet per minute. So it's rising at 140 feet per minute. And that is the answer to the question. Let's just relate it back to our steps. Did we understand the problem? Yeah, we kind of understood it, but we understood it more as we went along and started working it. Did we develop a mathematical model of the problem? That was drawing the picture and seeing, well, I think I can use a triangle and trigonometry in here. And I was definitely careful to distinguish constant quantities from those that change. Did I write an equation relating the variable whose rate of change I seek to the variable whose rate of change I knew? Yes. The rate of change I was seeking was dA to dt. So I wanted to relate the variable whose rate of change I seek, that was A, with the variable whose rate of change I knew, which was theta, because I knew d theta over dt. Once I had that formula, then all I had to do was differentiate both sides of the equation with respect to time. Then, once I had that formula, after I did the differentiation, then I could substitute the values for the quantities that depended on time, and I could put in my constant values, and then I had my solution, which I interpreted with the appropriate units. So this is a nice format to use right here to work on these problems.